section 6.5 in our trig course, our pre-calculus course. We're going to be talking specifically how to take a complex number and turn it into trigonometric form using sine and cosine. Now, sometimes when we talk about complex numbers, people think of just the number I, the square root of -1, but that's not entirely accurate. A complex number is ultimately, it's everything, it's all the numbers that you know of. A complex number, well, let me explain it this way. The difference between a complex number and a real number is the number I. If you take all the numbers in the world, and except for the imaginary ones, we have just the real number system. But once we add on the I, or the square root of a negative number, then we have the complex numbers. Okay, the first thing we want to talk about is graphing complex numbers. And you can see on the screen here, it looks like I've got the traditional coordinate plane. Well, you can see we've relabeled the axes as real and imaginary. Now that's just it doesn't work any different. It just has a different name. If we were going to graph 3 plus 4i, then literally I go over 3 and up 4. That's 3 plus 4i. Now, the first thing we discuss when we talk about complex numbers is the absolute value of a complex number. If you want to put that in real terms, it's just simply asking what's the distance away from 0 my number is. Well, if we were on a single number line, we just count the spaces back to 0. But in this case, we're in a two-dimensional axis, right? So we want to count away from 0, 0. So how far is it from the origin to my point? And that's exactly what we're going to do. You know, in previous sections, even in last semester, we talked about how to find distance on the coordinate plane, and it's just basically the Pythagorean theorem. If we have this kind of form, we have a plus bi. This is your traditional complex form. But when you see the absolute value symbol there, what it means is how far away from 0. So we do this, exactly a squared plus b squared, and then we square root it. Now, the trig form of a complex number looks like this. If you take a plus bi, then I want to be able to convert that into r times cosine theta plus I sine theta. So it's still kind of a plus bi in that same format, but instead of using a and b, we're going to be using a form of sine and cosine along with our r value, which is our radius or our absolute value. Okay, like I said earlier, r is just the square root of a squared plus b squared. We've already seen that one. And here's something else that we've already seen several times, especially with our vector section. We have theta equals tan inverse of b divided by a. No difference. That is exactly what we've been dealing with in the last several sections. Even before that, it's the same thing. If I wanted to find the angle between two sides or a coordinate or a vector or anything I want to do that contains this kind of axis, then we find our inverse or our tangent, our theta, excuse me, by tan inverse of b over a or y over x. Let's try an example. So the question here was find the absolute value, find the angle, and then write the trig form of 3 plus 4i. Well, r is this. We have 3 squared plus 4 squared. Then we square root that value. We get 5. Tan inverse is just going to be y divided by x, which is 53.13 degrees. And there's no magic formula. There's no working it out. There's nothing. It's just plug those two values into what we have for our complex form. 5 parentheses cosine 53.13 plus I sine 53.13 degrees, and that is my trig form. Now remember, I'm not trying to solve an equation. I just wanted to represent it in a different form. It's a number. It tells me, okay, go up 53.13 degrees from the origin or from x-axis, and then I want you to go out 5 units from the origin, and that's going to get me to the same location as it would be if I simply went 3 and then up 4 would be in the exact same location. So that's just another format. So don't think you have to plug this into your calculator, because if we actually type this in, we're going to get back to exactly what we started of 3 plus 4i. Now that we mentioned that, okay, go Going back to the rectangular form, a plus bi is rectangular, we just use these two formulas, which, here again, that is nothing spectacular, that is nothing new. You've seen that ever since we introduced the unit circle. And so this is simply reoccurring, which is a good thing, that you don't have to learn something brand new again. All right, let's keep going. Multiplication and division. Now you'd think with something of a fairly complicated form, it would be difficult to multiply and divide with these kinds of numbers. In fact, it's extremely easy. So what we're going to do is we're going to set two numbers. So z is traditionally denoted as a complex number, the letter for it. So z1, the first complex number, is r1 times cosine of theta 1 plus I sine of theta 1, and then z2 is the same thing with just 2's. We're going to go ahead and we're going to multiply these two values. And the formula for multiplication is really, I'm going to take the r values, you see them here, I'm going to multiply the r's together, and for theta, I'm just going to add. Now notice it's still in the r cosine theta plus I sine of theta form. Now you won't have all these pluses and stuff. You're going to actually multiply the two values together, and you'll actually add them together. Division, pretty much the same thing, except instead of multiplying, we're dividing our values for r, and we're subtracting our angles. Alright, so let's look at an example of that. So here's my two complex numbers. Yes, that is radians, and yes, if you ever have to calculate them, you should have it in radians. But we're not actually going to type it into the calculator. I simply wanted to add and multiply. So to multiply these values, z1 times z2, I would multiply 2 times 8 to get 16. And the angle, 2 pi over 3 plus 11 pi over 6, I would have to convert the 3's to 6's. And so you end up be 4 pi over 6 plus 11 pi over 6 to get 15 pi over 6. Okay, so there's my multiplication. Now to do the division, it's very cautious. I want to divide z1 by z2. So that means that 1 is going to be on top and 2 is on the bottom. That's a big deal because if it were z2 divided by z1, then my values would be very different. Okay, 2 divided by 8 is 1/4. That was 4/6 minus 11/6 to give me -7 on top. And so this is what division looks like. Remember again, division, we divide the coefficients, we're going to divide the r values, and we're going to subtract our angle. The order matters. Whatever comes first is on top, so that comes first. The very last thing we're going to look at is something called de Moivre's theorem. This one could be really ugly if I had to ask you to do this by hand. For example, a plus bi raised to a very large number. Well, that's FOIL as many times as you have an exponent. And if once you get past 3 or 4, it gets pretty long, and you really don't want to go into that kind of process. So this is what we do. If we can convert it into complex form, then the only thing we have to do is raise my r value to the nth power and multiply theta times the n. Okay, so we're not actually going to take anything specifically to a power other than my r value. Everything else is basically multiplication. So here, let's look at an example of this one. I have my initial value, or my initial number, -1 plus I squared root of 3. And I want to raise that to the 12th power. It's fairly big. Okay, so here again, I'm just using my formula, 2 to the 12th power, and then cosine of 12 times 120 plus I sine of 12 times 120. And if I actually type that right into my calculator, each part, one at a time, I find out that the cosine, this part becomes 1, and this part becomes 0. So we get 2 to the 12th is actually 4,096 times 1, and 4,096 times 0, so my answer ends up being 4,096. And you're saying, wait a minute, where did 4,120, where did you get all those numbers? Okay, let's go back. This is actually quite easy. Well, as we did earlier, I've given you a plus bi. You needed r to plug it in here. You also needed theta to plug it in there. We were given my n, which is 12. So I go back to my formulas, my basic ones. I plug it in, let it work out. I get 2. Tangent of inverse of square root of 3 over negative 1 equals negative 60. But whoa, where did the 180 come from? Remember, whenever your x value, or in this case my a, whenever it's negative, you absolutely, without fail, must add 180. Okay, go back to your notes about what we talked about with the tan inverse and how you found angles with that. You always, always, always add 180 degrees whenever you have a negative for your x or for your horizontal component. And so that gives me an angle of 120. I simply plug those in here and here, and I worked out each part separately, and then I multiplied through by my 2 to the 12th power. And that is how you use de Moivre's theorem. If you do not remember how to use de Moivre's theorem on the test or the quiz or things like that, it's going to be something where you won't be able to finish it in time. It is physically possible for me to multiply that together 12 times, but you don't want to do that. Okay, that would just be foolish, and it would be an evidence that you really didn't spend enough time studying. So make sure that you know how to use this formula. It's quite easy, but I'm pretty sure you don't get it on a formula sheet, so you'll need to memorize most of these formulas, if not all of them. All right, so this concludes the section 6.5, trig form of a complex number. If you have questions, please bring them with you to class.